an overdamped signal, your signal goes past what its asymptotic value or final value is going to be, and then comes back. It overshoots and then undershoots and then overshoots and then oscillates and then approaches your final value. Yes?
I'm on the Zoom and I don't see what's up there.
What do you see?
I see the previous problem.
Okay.
Okay, it's not underdamped.
There we go. I see it.
That is underdamped. Thank you, James. That is underdamped.
Oscillating one.
Yes. Yes.
Would underdamp be considered sinusoidal?
Yes. No, sort of. It's oscillating. It's not quite sinusoidal because it's sinusoidal would mean that it was periodic. You had the same thing through every cycle, and you don't. It is a combination of sines and cosines and exponentials. It does oscillate, but it's not actually considered sinusoidal.
Oscillation, got it.
Yep. Okay, so yeah, that is yes, that is underdamped. That is underdamped. Okay, so blank 1, you would fill in blank 1 with underdamped, and then I have a little less than or equal to. For underdamped, alpha is less than omega naught. Now, omega naught is what's called your resonant frequency, and alpha is going to be less than your resonant frequency. And then if we look at number 3 is critically damped. Critically damped means that it's approaching its final value as quickly as possible in the most efficient way, and that is critically damped. And the blank for number 3, which is 4, is that alpha equals omega naught. So when you have alpha equal to omega naught, that means that you are critically damped. Now, overdamped means that you are squashing it too quickly. It's overdamped, and so it's going to be below the critically damped in the charging situation. So in the charging situation, it's not getting to the asymptotic value as quickly. In the discharging, it's going to be the underdamped is going to be above the critically damped. Now, if you don't have the critically damped drawn, it's hard to tell whether something is critically damped or overdamped because they kind of look the same. Underdamped, you can tell. Underdamped is the one that's oscillating. But you can really only tell between critically damped and overdamped if you have them to compare to each other. Okay, and then in the second circuit, we can see that we are discharging, and so we're approaching 0. And blank 7, that one's going to be underdamped because it is oscillating. And underdamped means alpha is less than omega, so blank 8 is less than. Blank 9, that one is critically damped. It's following the quickest path to its final value, and that means alpha is equal to omega naught. And let's see, blank 10 is equal. Blank 11 is overdamped because it's not, it's going to take longer to get to the final value, and for overdamped, alpha is greater than omega naught. So any questions on that one? All right, so I am going to keep this problem, or keep this recording going and go on to number 4 on the same recording. And for this one, it says to determine if VC of t is overdamped, underdamped, or critically damped, given the following values, and then also to find VC of t. So the easiest way to do this is going to be using those formulas for that that I gave you that's on the front of the handout. And if you look at those formulas, you'll see that you have to determine if you have series or parallel. And then if you have series or parallel, depending on which one you have, you're also going to have to find some values like IC of 0, VC of 0, and VC at infinity, or VL of 0, IL of 0, and IL at infinity. So the first thing we have to do is to figure out what kind of circuit we have. And we want to look at what it's going to look like after we open the switch. So after we open the switch, what kind of circuit are we going to have, parallel or series? And after we open the switch, right here, this side of the circuit is not going to matter anymore. It's not going to be connected. It'll be open. So after we open the switch, we're only going to have the circuit that I have drawn here. So is that series or parallel?
Series.
That one is series. So we know we're going to have series. So when we look at our series, we see that we're going to need VC at infinity, VC at 0, and IC at 0. So VC at infinity, VC at 0, and IC at 0. We can do that first, or we can figure out if we have overdamped, underdamped, or critically damped first. I think let's do the critically damped or overdamped or underdamped first. So it's series, so alpha is R over 2L. So alpha equals R over 2L. Now, which R do we use? We use the R that's going to be the resistance that's in the circuit at the time that we are actually finding it. So that's after t equals 0. So that in this circuit, that would be R2. So R2 is 1.2 ohms.
Is it BC of 0 or is it BC of 0 minus?
Is there a difference?
No, it's not.
Because it's a capacitor. If it was an inductor, it would matter, because VC, a voltage across a capacitor, cannot change instantaneously. So VC of 0 minus equals VC of 0 equals VC of 0 plus. Now, IC of 0, well, that is another story. This is IC of 0 plus.
Ah, I see. Okay. That's why I always mention when they can't change instantaneously, depending on which component.
That's right. So like if you look at your inductors here, your inductors, you have IL of 0 and VL of 0. Well, the IL of 0, that has to be the same. IL of 0, IL of 0 minus, IL of 0 plus, those all have to be the same. VL of 0, that could be different, and what they mean by that is VL of 0 plus. So the IC of 0 is IC of 0 plus, the VL of 0 is VL of 0 plus. The others, they have to be what they are. Okay, and we were saying over 2L, and L was 0.1 Henry, so over 0.2, so alpha equals 6. And then omega naught always equals 1 over the square root of LC. That's our resonant frequency. So that'd be 1 over the square root of L is 0.1 and C is 0.1. So that's 1 over the square root of 0.01, which is 1 over 0.1, which is 10. So omega naught equals 10. And so we have alpha is less than omega naught, which tells us that we are in our underdamped situation. So in the underdamped situation, let's see what all we need to find to get our answer. We need to have alpha. We've got alpha. We know what alpha is. Alpha is 6. We need to have this omega D. Omega D only happens for the underdamped situation. Omega D is omega naught squared minus alpha squared. So omega D is 10 squared minus 6 squared, or 100 minus 36, which is 64, which is 8. So omega D is 8. Yes?
It's just asking if it's overdamped, underdamped, or critically damped. So is that like actually asking?
Well, then it says find VC of 0. I mean VC of T.
I'm tripping. Sorry.
Yeah. No, I typed it in. I mean, it didn't originally say that, but I added it to the question. Yeah. So yeah, no, we wouldn't have to do this. If all it asked is it critically damped? Yeah, you could stop.
Okay.
Yeah. But yeah, I wanted to practice this. Okay, and then, so we've got omega D now. Now we need to find D1 and D2, and D1 and D2 are asking us some things about our circuit. So we need to go back and look at our circuit, and we look at it at 0 minus. And so even though I was saying earlier that it's the same at 0, or the voltage across the capacitor is the same for 0 minus or 0 plus, you find it by looking at 0 minus, because you can't predict what it'll be at 0 plus without knowing what it was at 0 minus, and so we have to do that first. So we're going to take this and look at it at 0 minus. So at 0 minus, we assume it had been like this for a long time, and when it has been like this for a long time, the inductor acts as a short circuit, so it's just a straight wire, and the capacitor acts as an open circuit. So we need VC of 0 minus and IL, or IC of 0 minus. Well, IC of 0 minus is easy. It's an open circuit. It has to be 0. But just because it doesn't have a current through it doesn't mean it doesn't have a voltage through it. And it, in fact, across it. It does have a voltage. The way you find the voltage across something is you find something it's in parallel with. So anything it's in parallel with will have the same voltage. So V naught was given to be 12, and R1 is 0.4, and R2 is 1.2. And so the capacitor is in parallel with R2. So if I can find the voltage across R2, then I know the voltage across the capacitor. The way I would do this now is by voltage division. The way I would have done it would have been to use V equals IR to find the current, and then take the current times the resistance to get the voltage. Either way is fine. There's not a right way or wrong. Well, I take it back. There are lots of wrong ways. There are an infinite number of wrong ways, but there are also quite a few right ways. Yes?
When would you not have to use voltage division? And just like, oh, it's parallel, that means it's equal to it. Does that mean, is that only if there's no resistor between it?
Yeah. Well, but it doesn't, here it wouldn't matter if there is a resistor here or not because it's open. But like if I had, let's see, if I had,
Like Well, I'm saying, does R1 affect it?
Yeah, because of voltage division.
Okay.
Yeah. So if R1 were not there, the voltage across R2 would be the same as V naught, would be the same as the capacitor.
Okay.
But R1 is there, so that means the voltage across R2 is part of 12. So we start at 12 volts, we lose some as we go across 12 R1, we lose the rest as we go across R2, and then we're back to 0. Okay, so V across the capacitor has to equal V across R2, which has to equal our total voltage change times the resistance of R2 over the sum of the two resistances, which is 1.6. That's voltage division. So voltage division says the voltage across R1 equals the total voltage times R1 over R1 plus R2. So that's 12 times 3/4, which is 9. So VC of 0 is 9. Now we need to find VC at infinity. So let's go back and look. This is our circuit after the switch has been opened. Are there any sources in this circuit? There are no sources. So eventually any energy that was stored in the inductor or capacitor will get dissipated through the resistor, and then eventually we'll have no energy left and no voltage left. And so VC at infinity will be 0. So now we have all of the values we need to write our equation. So we have D1 equals VC of 0 minus VC at infinity. That was 9 minus 0 equals 9. D2 equals 1 over the capacitance, which I could look up, but I see it's multiplied by IC of 0, which I know is 0. So I'll take the lazy way out because I know the answer is going to be 0. Plus alpha is 6 times VC of 0 is 9 minus VC at infinity is 0 over omega D, which we found to be 8. So D2 is 54 over 8, which is 6.75. Is it? Yes. Okay, so that means VC of t equals e to the minus 6t times 9 cosine 8t plus 6.75 sine 8t plus VC at infinity, which is 0. Any questions on that one? Okay.
Oh, I did.
Yes.
Sometimes I saw on one of the examples that we had in class, it asked for VC of t and IC of t.
Good
which
question.
I had no idea how to do that.
Excellent question. Okay, so what you have to do for that is go back to here, where you see that I of t equals C dV dt. So you find V of t the way we just did. And then if you had to find I of t, so we have this nice, not so nice, but there it is, function for VC of t. So I of t equals C dV dt. So then you would take the value of C, whatever it was, and then you take the derivative. And this,
The derivative of that huge function.
it's not as bad as it seems because it's a product rule, but let me just show you why it's not as bad it appears. So it was e to the minus 6t cosine 8t plus, or 9 cosine 8t plus 6.75 sine 8t. Okay, so I've got this c out in front, and that'll stay there. And then the product rule, if you remember, is f prime g plus f g prime. So the derivative of e to the minus 6t is minus 6 e to the minus 6t, 9 cosine 8t plus 6.75 sine 8t, plus e to the minus 6t times the derivative of the second one, and then the derivative of cosine is minus sine, chain rule, you take the 8 minus 72 sine 8t, and then the derivative of cosine is sine, so plus cosine 8t, and then the only hard part is multiplying 8 times 6.75, which I can't do that. That's something.
Wouldn't that be 48 plus 6?
50, wait, the points.
54?
That's 54.
3/4, I'm not thinking about it, I can't do that. Yeah, but then actually, once you did that, you actually have like terms that you could combine, and it simplifies a little bit. But yeah, it's really not, you look at it and you think, ugh, I'm not taking the derivative of that, but that was it, that was all it is. So it's not as bad. Yes,
So I had a bit of a question earlier at the beginning.
Yes.
Here, I think it was, yeah. So you said the voltage across it's like VL, of 0 equals.
VC, these are all C's.
Oh,
They look like L's, but they're C's.
okay, so it was all saying the voltage across the capacitor is the same across each iteration of the circuit. I was
Mhm.
wondering,
No, just at 0, 0 minus, and 0 plus. After you get past 0, it certainly changes.
yeah, so I got how at 0 minus and 0 it's going to be the same
Yeah?
because once you flip the switch, that the voltage that was stored there becomes the voltage source. I was wondering. Well, so it says V0 plus. That's. I'm sorry. Can you scroll up again? I'm pretty tired. But whenever you say the voltage of the capacitor at 0 plus, are you saying that like at infinity, or is that what you meant, or?
I mean, right after switch action. I use 0 plus. I think that your instructor doesn't use 0 plus. I use 0 plus to mean limit as you're approaching 0 from the right.
Oh, so it's like the positive edge versus negative edge.
Yes,
That makes sense. Yeah.
Yes.
Okay.
yes.
Um,
And I also realized I made a mistake when I said that IC of 0 was 0 because it was 0 at 0 minus. That's not what I needed to look at. I needed to look at IC of 0 plus. I lucked out, and it turned out to be right. Let me go back to this, because this is important, because I could have been wrong, and that would have made the whole answer wrong. Because the VC of 0 has to be the same before and after. That has to be VC of 0 minus. IC of 0 does not necessarily have to be IC of 0 minus. It could be, but it doesn't have to be, because it can change instantaneously. Now, at 0 minus, it was definitely 0 because it was open. At 0, it was also 0. Why?
Because the inductor had 0 as a 0 minus.
Because the switch was open.
Well, this was when the switch is closed. I've now closed the switch. I mean, I've opened the switch. The switch, sorry,
But
the switch was.
at
The switch is
IC
now
0,
open. The switch is open, but the current through the inductor was 0 at 0 minus, and the current through the inductor cannot change instantaneously. And so, since the current through the inductor cannot change instantaneously, then the current through the capacitor had to be 0. Now, that would be entirely different if we had a circuit that looked like this. And you very well might have a circuit that looks like this,
Oh, because it's in series.
because it's in series. Okay, let's say this was our circuit. Let's say this was our circuit. Let's just say it is.
Okay.
Okay, here, I have to have another resistor there. I'm making that 2 Henrys. I'll make this 1 farad. I'll make this 5 ohms, and I'll make this 10 ohms. Okay, this let's look at this one. I think this is important. All right, and let's make this 12 volts. Let's look, and this is switch action T equals 0. Let's look at 0 minus. So at 0 minus, what is VC of 0 minus? What's it in parallel with?
It's in parallel with voltage source.
Not in parallel with the voltage source,
No?
just with a wire. It's not in parallel with the voltage source because I have a resistor right here.
Okay.
So this is open, so this resistor is not doing anything. But it's not in parallel with the voltage source because this resistor is in the way between it's and the voltage source. It is in parallel with the straight wire. What's the voltage
just-
drop across a straight wire?
0 volts.
0.
You said it's not in parallel because the resistor, but we have the same exact resistor, but now it is in parallel with the straight wire. I don't get that.
It's not the same exact resistor. The resistor from before was in a different place.
Like I'm saying in that one example, so we're saying it's not in parallel because there's a resistor between voltage source and capacitor where it's at, right?
It's this resistor that makes it not in parallel. This resistor we don't care about
Oh,
because there's no current through this resistor.
I see. All right, I understand now.
You want to argue with me some more? Huh?
Yes, I
Okay, all right.
was so confused.
But now you get it.
That was because no current. That's why.
No current. Okay. It's in parallel with this straight wire. What's the voltage drop across the wire? 0. Okay. What is the current through the capacitor? Right at 0 minus.
0.
0. All right. What is the current through the inductor? What is IL of 0 minus?
1.2 amps.
1.2 amps because I have a voltage source of 12 and a resistance of 10, 1.2 amps. What is IL of 0?
1.2 amps.
1.2 amps. Now, if I am defining IC as being the current going this direction, all right, now let's look at IC of 0. So now we have opened the switch. What is, we know IL of 0. IL of 0 we said is 1.2 amps. What is IC of 0?
Negative 1.2 amps.
Negative 1.2 amps. Why negative?
Opposite direction.
The polarization is the opposite.
Yeah, it's going the other direction, right? Okay, so see, in this instance, IC of 0 is not the same as IC of 0 minus. And so in the problem that I worked for y'all, I lucked out because I just looked at it and said, oh, look, IC of 0 is 0 because there's no current flowing through it, and forgot, it's like, no, I can't do that. I got to look and see because it could have changed at switch action. And I don't know how many more times to tell you that's important. Okay.
Is that because we can choose what IL of 0 is? Or I mean, we can choose the direction of IL of 0 ourselves? Because it's an inductor?
No, is that you can't. IL of 0, it was given to us in this one, but what do you mean we can choose?
I'm sorry, I'm conflating chapter 7 with chapter 6. I'm thinking of Li of L of 0.
Yeah, so no, I used the direction that was given to me. So the reason I'm not quite sure what your confusion is, but I used the directions that were given to me, and I said that the direction was given to me for IC was going down like this. And since IL was going in this, I know IL can't change, and IL was going in this direction, and IC is going in the opposite direction, so it's negative. Okay, other questions before I stop this?
Yes.
Yes.
Well, actually, Ryan, do you have how does someone derive all of these equations for the overdamped, critically damped, and such in the first place? Where do they get those from?
Solving the differential equation. Unfortunately, you aren't able to come to my 9:30 session because I think I did one. Didn't I do one, James?
I believe so.
I think I might have done one. Yeah,
Well-
you solve the differential equation. So I won't go into it right now, but if you go back and look at one of the videos, it's in there. Yeah. So
What were you at? What was the question? What was the?
the question was, where do those equations come from, the alphas and the omegas? You remember the day that we started doing Laplace transforms? And I said, and I drew out the circuit, and I showed that I did a KVL, and I showed that you ended up with a derivative, and then a second derivative, and a differential equation, a second order differential equation.
Yes.
Yeah,
Yes.
so it's in there somewhere. Okay. And it's good stuff to know, like whenever you're going to interview for your jobs when you become electrical engineers, because sometimes they ask you real kinds of questions about it. All right, so let's go on